Right, so we are now going to look at the very last section of this chapter, which is acid-base indicators. Now, what is an indicator, first of all? It's a substance that changes colour according to the pH of a solution when it is added to it. Usually they're weak acids, sometimes they're weak bases, and the key thing here is that the colour of the dissociated molecule is different from that of the undissociated molecule. So the colour of the acid is different to the colour of its ions. So for the ones that are weak acids then, what does that look like? So here we're using HA to represent the colour of the weak acid indicator, and then when it dissociates it forms the ions H plus and A minus, and we are going to look at both of those. So the acid itself is red, and when it dissociates it turns blue. Now, what will happen then if you add some acid in here? So if you were to add acid to this particular indicator, you'd be adding a source of H plus ions, and those H plus ions would cause the equilibrium to move over towards the left. If the equilibrium shifts towards the left, then you're going to get a red colour in this indicator. What would happen then if you were to add some OH minus ions? So if you were to add a base, it's a funny one this. The OH minus ions will actually react with the H plus on the right hand side, and they'll form water. Now the net result of that is that they're reducing the amount of H pluses on that right hand side, and from our study of equilibrium we know that the equilibrium will shift to counteract that change, so it will move over towards the right in order to produce more H pluses. So the colour change will be to blue. Now, what happens when you're looking at a base? So some indicators, not very many, but some indicators are actually weak bases. Here's what the dissociation looks like for a weak base. So you have your BOH to represent the base itself, and it dissociates into B pluses and OH minuses. And of course the key thing is that the BOH is a different colour from your dissociated form. In this case the BOH is blue and your dissociated form is red. Again, we're going to look at what would happen if you add acid to this. So if you add H plus ions in here, they're going to react with those OH minus ions on the right to form water. Net result of that is that you're removing those OH minus ions from the equilibrium. And if you remove those, the equilibrium of course will shift to the right to try and replace those OH minus ions, and you'll get a red colour. What will happen then if you add a base? If you add a base, you are putting in OH minus ions, so you're increasing the concentration of those on the right hand side there, and if you do, you will drive the equilibrium over towards the left in order to use them up, and if you drive the equilibrium to the left, you'll get the blue colour of the BOH. Now, you were always told, of course, when you're doing titrations to only use a very small amount of the indicator, and the reason for that is you don't want this H plus and OH minus, these ions, contributing to the result of your titration. Now, next thing we're going to move on to is the pH range of indicators. So the pH range of an indicator is the pH interval over which there's a clear colour change for this indicator. Here are the three main indicators that you'll have encountered so far. You've methyl orange, litmus, and phenolphthalein. Now, the approximate pH range is listed for each of them. I suggest you just learn this off. It comes up over and over. You'll need it for your titration question if it's an acid-base titration. So methyl orange then, its pH range is 3 to 5. If the pH is lower than 3, it is a red colour. And then if the pH is greater than 5, it's a yellow colour. So the pH change there is 3 to 5, and the colour change is red to yellow. Litmus has a pH range of 5 to 8, that's where it changes colour, and it goes from red to blue. And phenolphthalein then has a pH range of 8 to 10, and it goes from colourless to pink in that pH change. So just a summary of that, your methyl orange, if you're below pH 3, it's red, above pH 5, it's yellow. Litmus, if you're below pH 5, it's red, and above pH 8, it's blue. And phenolphthalein, if you're below pH 8, it's colourless, and above pH 10, it's pink. Now, of what use is that? Well, we're going to compare that now with some titration curves. So, pH ranges are found out by carrying out a pH titration. The theory behind this is that you start off with an acid and you add a base to it until you get a change. So measured amounts of alkali are added to a volume of acid, and you have a pH sensor inside in this acid, and it is logging the pH as you add the base. Okay, that's what the setup looks like. And as it logs the pH, it will plot a titration curve for you. Now, what do these pH titration curves look like? So if you were to add a strong acid, start out with a strong acid and add a strong base, for instance, hydrochloric acid. If you start with hydrochloric acid and you add some sodium hydroxide to it, here's the type of pH curve that you're going to get. So again, just to recap, you're measuring the pH as you add your sodium hydroxide into your hydrochloric acid. So plotting here on the x-axis, we have the volume of sodium hydroxide that you've added into your 25 centimeters cubed of 0.1 molar hydrochloric acid. So your hydrochloric acid is starting out at a pH of 1. You'll see that going up on the y-axis. And as you add more and more sodium hydroxide, you're getting a gradual increase in the pH until you reach 25 centimeters cubed of that sodium hydroxide. And the pH jumps dramatically from 3 up to 10. Now, that pH change happens with the addition of just 1 drop of your sodium hydroxide. So it's a dramatic change in pH. What does that mean? It means that your endpoint is really easily detected. You can use any one of the 3 indicators for this particular titration. Methyl orange will show a colour change, litmus will show a colour change, and phenolphthalein will show a colour change within that pH range of 3 to 10. Of course, you know methyl orange changes between 3 and 5, so it'll change from red to yellow in this titration. Or litmus, it changes between 5 and 8, so it'll show a change from red to blue. And your phenolphthalein, it changes between 8 and 10. So when you're at your pH 3, it'll be colourless, and when you suddenly jump up to pH 10, it'll change to pink. So the net result of that is that any one of the 3 indicators that we've studied would be suitable for this titration because they will change colour in that range, in that pH jump from 3 to 10 that you achieve by adding just 1 drop there of sodium hydroxide in and around the 25 centimeters cubed mark. So suitable indicator for this, any that has one colour below pH 3 and a different colour above pH 10, which means any of the 3, methyl orange, litmus or phenolphthalein. Now if we're to change that up a bit and look at a strong acid versus a weak base, so our example for this would be again your hydrochloric acid, but in this case we're adding 0.1 molar ammonia into it. Okay, so again you're starting out at a pH 1 because you have your 25 centimeters cubed of 0.1 molar hydrochloric acid, and you're gradually adding ammonia to that. And the pH is gradually changing until you get your endpoint, and it suddenly jumps from pH 3 up to pH 7. Now there's only one of our indicators that have a suitable change that suits the pH change that you get there, the dramatic jump from 3 to 7, and that's the methyl orange, because methyl orange is red below a pH of 3, and then once you get above a pH of 5, it changes to yellow. So it will change from red to yellow in that range that you have there with your strong acid versus weak base. Now, what about a weak acid versus a strong base? And we're going to use our usual example for a weak acid, which is our ethanoic acid. And so if you start out with 25 centimeters cubed of a 0.1 molar ethanoic acid, and then you add 0.1 molar sodium hydroxide, the pH will go up gradually, and then all of a sudden there'll be a jump from pH 7 up to pH 10. And the only indicator that has a distinct colour change between 7 and 10 is your phenolphthalein, and that's why you select the phenolphthalein for this one. And the final pH curve then is a weak acid versus a weak base, and this is a very unusual looking curve. So if we were to have 25 centimeters cubed of 0.1 molar ethanoic acid, and we were to gradually add in our 0.1 molar ammonia, which is a weak base, we will see that there is no sudden jump in pH. It's all a kind of a gradual change. What does that mean? It means that there literally is no indicator that we can use for this. So we've no suitable indicator because the pH rises so gradually that it's not possible to detect the endpoint with an indicator. And that is the end of this chapter. Thank you.